Good afternoon, all of you. I am Dr. Pavitra Singh. I am working as a technical fellow and consultant with Dyne 3D Technologies, Singapore. So, actually, I am going to deliver my talk on the topic gas solid hydrodynamics and heat transfer characteristics in a rotating fluid bed reactor. So, first, I would like to introduce the principle of drawing. So actually drying is nothing but it is a process of moisture removal, and you can see in this figure food grain particle is kept on the flat surface. So actually hot air is supplied across this food grain particle. First the moisture of this food grain particle evaporates, then it carried away into the surroundings, and we can calculate the rate of moisture content by using the formula given by Jaman and Bala in 2001. dm upon dt is equal to minus Ka mg minus me, where me is the equilibrium moisture content and mg is content of the grain. K is constant, A is surface area. So this drying process actually completes in two regimes. First is the constant rate period A to B, and second is falling rate period B to C. So I would like to talk about constant rate period A to B. So actually during this period grain remains still wet, and free moisture from the grain surface is evaporating, and B is the point of critical moisture content. At point B the moisture removal rate ceases to be constant, and further falling rate period starts from B to C. So during this falling rate period, the vapor pressure of the particle surface falls below the saturated pressure, and the internal moisture of the particle start evaporating during this falling rate period. So this graph is given by the Mazumdar in 2007. So actually I would like to discuss about the advantages and application of this rotating fluid bed reactor. Actually, this is a very compact size reactor through which a large amount of air interacted with solid particles, and due to higher solid slip velocity, higher heat and mass transfer is possible, and this higher heat and mass transfer makes the drying process faster. So we can perform various operations in this reactor such as particle coating, milling, separation, mixing, gasification, combustion, drying, and I am trying to use it as a milk dryer. So I am developing a device for the instant milk drying, means liquid to powder, and I performed various operations in this reactor as a dryer for the drying of black pepper, coriander, paddy, tea, wheat, peas, etc. So you can see I performed one simulation on this reactor. So here air is entering through these tangential air inlets. These are 16 air inlets, and this is the solid bed region. Is it visible? And this is chimney outlet. So I will discuss about this reactor in the next slide. So actually fluidization is nothing but it is a technique of making solid particles behave like a fluid. So actually for the perfect fluidization, three forces should be in balance: centrifugal force, gravity force, and drag force. If these forces are not in balance, then fluidization in this reactor may not be possible, or maybe partially fluidized, or fluidization may be collapsed. So we have to balance these three forces. Actually this concept of rotating fluid bed reactor has given by the D. Wilde and Brockule in 2007. So actually this is a rotating fluid bed dryer I have developed in my lab at IIT Guwahati. So actually this is electric motor, this is air blower, this is coupling, this is air bypass valve, this is air control valve, this is orifice, and this is CO2 manometer, and this is the air heating device, and this is air distribution chamber, and these are multiple air inlets, and this is main vortex reactor. So actually air is entering in this vortex reactor in transverse direction, and in the blue color you can see this is the blade slit, and it is separately shown in this figure, you can see. So this blade slit is diverting the air in the tangential direction. So first we have to create the vortex in this reactor by injecting higher velocity. So confirming the vortex in this reactor, we need to inject the solid particles, and these particles follow the gas path partly and form a rotating solid bed. So you can see in this figure, so this is actually rotating solid bed. So paddy grains are here. So this is actually solid bed region, and remaining part is called freeboard region. So in this extended figure you can see in the green color, air is entering into this reactor via these air inlets in tangential direction, and this is leaving this reactor via chimney outlet continuously, and the solid particles in this solid bed region are rotating in the form of solid bed till the end of the process. So here you can see air is entering continuously and leaving this reactor continuously by the chimney outlet, while the solid particles are rotating in the form of bed till the end of the process in the case of drying. So here you can see this is solid injection system, this is solid outlet, and remaining part I have already discussed. So in the three-dimensional view you can see these are the solid particles in red color, and this is the front view. So for the design and development of this reactor, I have used the important correlation given by Kochitov 1969. He has given one relation, force ratio lambda is equal to centrifugal force upon drag force, and lambda should vary in the range of 0.025 to 0.038, and you can see the direction of gravity force is vertically downward in each and every location, while the drag force is toward the chimney outlet, and the centrifugal force is acting towards the chamber wall. So single particle is selected in this bottom location. You can see the centrifugal force is acting toward the chamber wall, and means vertically downward, and gravity force is acting vertically downward, and the drag force is acting toward the chimney outlet, means in the upward direction. So this is the principle and working of this rotating fluid bed reactor, and I use this reactor as a dryer, and now I am using this reactor as a milk dryer, instant milk dryer in the present research. And this is actually rotating fluid bed dryer with the slit, and this is rotating fluid bed dryer without slit. So actually the basic difference between this and this is the use of slits. So in first case I use the blade slit, you can see in blue color, and in the second case there is no slit is used. So in the first case air is entering in transverse direction and it is diverted by using slits, but in second case I use the inlets in directly in tangential direction. So there is no need of blade slit because blade slit is costly and it is making the system complex. So this is cheap in cost because we are not using costly blade slits, and complexity is also reduced. So this is best suitable dryer. So this is the pictorial view of RFB SG with slit, and this is without slit. So these are two setups. So this is with slit, and this is the rear view of this setup, and this is the setup without slits. So the basic difference between these two dryers is the use and application of blade slit. So in first case you can see air is entering in transverse direction via circular air inlets, and in second case air is entering via the air inlets of rectangular cross section. So in second case the cross sectional area of the solid bed and the cross sectional area of the air inlet is similar, you can see in this figure. So due to similarity of the cross sectional area of both air inlet and the solid bed region, the uniform bed is obtained. So due to bad uniformity, higher heat and mass transfer is possible in this reactor as compared to the first one. So first one is costly, and you can see at the corner points the air interaction with particles is poor. In this red circle you can see, because air is entering via the circular cross-sectional inlets, and it is converted into the rectangular cross-sectional inlet. So this is taking time in milliseconds. So due to poor connectivity of air with the solid particles, this is less effective than the second one. So I have selected this reactor for the further study. So this is the formulation used in this calculation. So we can calculate the tangential average radial gas velocity by using formula UR is equal to Fg upon 2 pi RL epsilon G, where Fg is the total gas flow rate, L is the length of the reactor, length of reactor is this one. And we can calculate the radially outward centrifugal particle acceleration by using formula AR is equal to R omega square is equal to Vt square upon R, where omega is angular velocity, Vt is the tangential velocity, and Fg can be calculated by using formula Ng rho g as UZ. Ng is the number of gas inlets, and rho g is density of gas, as is surface area, and UZ is velocity of gas. And now we can calculate tangential momentum introduced in the reactor by using formula mt is equal to Fg Uz, and we can place this value. So we will get mt is equal to Ng Sc rho g Uz square. And during the experimentation we need to calculate the percentage of moisture at a certain time interval. So I have selected the time interval of 5 minutes. So I have selected the samples after 5 minutes in each and every 5 minutes. So we can calculate this moisture content percentage by wet basis and by dry basis. So we can say this is equal to Mi minus Mf upon Mi into 100, and in second case it is Mi minus Mf upon Mf into 100. Mi is the initial moisture content in the grain, and Mf is the final moisture content in the grain. So we can use these two formulas either on wet basis or on the dry basis. So actually this is the simulation model of this RF-BHE reactor. So you can see a finite volume method is used, and formulation used is first order of Bin so for the unsteady, and discretization of convergence fluxes is first order of Wien, and this is actually three-dimensional model, and phase coupled simple algorithm is used. This is given by Vasquez and Inovo in 2000, and you can see this is the inlet of dimension 6 mm thickness, and this width is 50 mm. This is called length of the reactor. So this is 50 and this is 6 mm, and this is the chimney outlet. This is spiral chimney outlet actually. So this length is 70 mm and this is 50 mm. So this is the chimney outlet. So actually air is entering in this reactor, creating vortex and leaving this reactor by the chimney outlet, and solid particles will be in this location. So this is the boundary condition used for this simulation. So at the inlet, outlet, right wall, left wall is given there. So at the inlet for the gas phase there is no slip, and for solid phase free slip is there, and at the outlet pressure will be atmospheric, and for the right wall, because it is stationary, so there will be no slip for the gas phase, and zero shear stress will be for the solid phase. Similarly for the left wall, same boundary conditions will be there. So these are the parameters used in the simulation. So actually this is a multi-phase model, so that's why I applied Eulerian approach with kinetic theory, and the time step used is 0.001 second, and convergence criteria is 0.0001 for the momentum, and for energy it is 0.00001, and under relaxation factor is 0.5 for the pressure, 0.2 for momentum, and 0.2 for volume and granular temperature, while the maximum solid packing limit is 0.63. And this is the details about the gas and solid phase. So the density of gas is 1.2250 kg per meter cube, and for the solid it is 800, and thermal conductivity is 0.0242 for the gas phase, and for solid it is 0.045, and specific heat capacity is 994 for the gas phase, and 800 joule per kg Kelvin for the solid phase. So these are the boundary condition parameters used in simulation and the gas solid phase details. So this is the procedure actually for the simulation. So I have selected transient model because velocity is very high. I have already calculated by using Reynolds number. So this is means gravity effect is considerable because particle is having weight, its weight, so it will be minus 9.81, and I use the multi-phase Allen approach, and energy equation is applied, so this energy is on, and this is the boundary conditions. Actually I have used 8 air inlets, so for each and every air inlet I applied the velocity and the temperature separately, and then I have selected the solid in the geometry, means reactor, and then patch, and use the volume fraction 0.58. So then I run the calculations, and I got this result. So you can see this graph. One minute. So actually this will take lots of time, so I am skipping. So actually there are 5 models for the simulation for the multi-phase flow. So actually there are Seller and Newman drag model, Venn and U model, symmetric drag model, Glasgow drag model, and Sambal O'Brien drag model. So actually for the present problem, these 2 drag models, Glasgow and Sambal O'Brien models were best suitable. So I performed numerical study on these 2 models. So this is for the Glasgow model, and this is the result from the Sambal O'Brien model. So you can see the volume fraction of solid is very dense, very high before the entry of the air in the reactor, and bed thickness is also less as compared to the second one. So in the second case you can see the bed thickness of the solid is higher, so volume fraction is also means homogeneous as compared to the first one. So you can see both the bed thickness and the means uniformity of the solid volume fraction is best in the second case. So I use this Sambal O'Brien model for further study in details. So I performed the grid independence test for the 3 grid size for 80,000 grid cells, 94,500 grid cells, and 610 grid cells. So for the suspension density is plotted in this graph. So the variation of suspension density for these 3 grid size G1, G2, G3, you can see the results are almost same for these grid size, but for the G2 and G3 results are very close, and I use this grid size G2 because it is taking less time as compared to the grid size G3. So I use this grid size for further study in details. And you can see this is the variation of volume fractions. So actually I have selected four directions, I have selected various points in four directions. Suppose this is selected at 35 mm, 94 mm, 96, 98, 100, 102, 104, 218. So at various points I have selected P1 to P16, and this right to chimney outlet direction, top to chimney outlet direction, left to chimney outlet direction, and bottom to chimney outlet direction. So in all these four directions I have selected these 16 points to measure the pressure, temperature, velocity variation, volume fraction, suspension density, etc. Also I selected 8 points in the radial direction to measure the variation in the radial direction. So you can see in this figure, in the free bed region the volume fraction is almost 0, and in the solid bed region variations are minor. So actually when the air is entering in this reactor, the volume fraction is suddenly decreased because impact of air. So again it is increased in the bed thickness of 112 to 114 16 mm. Again this is decreasing in the bed thickness of 98 mm to 112 mm. So in the four different locations you can see in the right direction means right to chimney outlet direction by color black, and top to chimney outlet direction in red color, and left to chimney outlet in the green color, bottom to chimney outlet in the blue color. So variations are given in this figure, you can see as per the color coding. So I actually scale up this reactor by increasing the diameter first, then I scaled up this reactor by increasing the length. So actually in the previous case I found that the bed thickness was very thin when I increased the diameter of the reactor. Actually we can increase the volume of the reactor by increasing the diameter or by increasing the length. So I have only two options. So when I increase the diameter, the bed thickness was very poor, means thin. So I preferred the increase the length. So I increase the length 50 mm to 200 mm in the second case. In third case I increase the length 250 mm. In fourth case I increase the length 300 mm, and further I tried to 350 mm, but results was very poor because in the direction of length the volume fraction of solid is decreasing or very non-uniform. That's why I preferred the maximum length of this reactor 300 mm. So the maximum capacity of this reactor was for 3 kg of drying for the 15 minutes, means 12 kg per hour, and 96 kg per day for 8 hours. So this is the means scale up and optimization of this RFBIG reactor. Thank you. Hello. Yes, sir. Pardon? Efficiency. Actually, sir, rotating fluidized bed dryer is very fast drying technique, and at laboratory level it is not efficient for the cheap cost food grains, but for the higher cost food grains it is very suitable. because sir, it is taking only 10 to 15 minutes to dry a product, while the conventional methods are taking 2 hour, 1 hour, or 2 days also in the sun drying. No, actually, this is a reactor with static geometry. Drum is not rotating, sir. Only only high velocity air is injected into the reactor, and it is creating vortex. And confirming the vortex, we need to inject the solid particles, and these particles follow the gas path partly, and forming a rotating solid bed. So no moving part is there. It is totally static geometry. Yeah, sure, sir. Welcome. May I close the meeting? Okay. Okay.